All right, guys, so let's see, some news about next week. So I'm still waiting to hear back about room availability for this informal review session next week, so I don't know yet what it's going to be. I also thought I would toss in some extra office hours during finals week. I haven't figured those yet out either. I still got to write this dang final. It's going to be a pain. But I'm going to send out a giant email which has basically all the info that you guys need to know about what's going to be available during finals week, about the extra office hours. As usual, I'll put out a study guide like I've done for the midterms. I'll put out practice problems, and yeah, I'll try to get that out by Friday, I guess. And on Friday, by the way, so if you look at the class schedule, it says we're going to be doing a review here. So on Friday, one thing I'll do that's important is kind of give you an idea of what your cheat sheet should include. So I'll kind of go over all the formulas we've done in this entire class. So yeah, I guess that's what I have to say about that. Any questions on anything?
Yeah. Is the review session going to be podcasted? Or is it it's not in this room, or is it in the small room?
I don't know. I could request that if I remember to.
This is a Friday evening.
The review session? Yeah. Oh, I don't know the time for that. Not the informal one. On this Friday during normal class, I'm going to review some stuff too. But yeah, okay. So the informal review session, by the way, which will probably be Wednesday or Thursday. The idea really is for you guys to bring questions in for that. So that's really how it'll work best. It's kind of it'll be pretty good if you've been studying all week long and there were still a few things you couldn't figure out, then just bring them to the review session. I'll probably pick on some of you guys and make you answer questions and stuff, which is how you learn, so you should hope you get called on. All right, so let's finish this off now. Last section in the class, Taylor series. So, let me refresh your memory on the main formula for this section, which is the formula for the Taylor series of a function. Recall the Taylor series formula, which is f of x equals the sum from n equals 0 to infinity of nth derivative of f at c over n factorial times x minus c to the n. Okay, so yeah, we're going to talk some more about this today. So let's do some examples okay, a lot of your homework problems will just straight up ask you to calculate the Taylor series. It's something you should know how to do. A lot of times, though, there's sort of tricks or shortcuts that you can use. You could just straight up use the definition, or sometimes you can use a little trick or shortcut. So how about let's find the Taylor series for f of x equals x squared plus 1. And I didn't say where I wanted it centered. So let's say centered at, say, x equals 0, okay? Right, i.e., so c is 0. Here, let me just say it like this. Centered at 0. Okay, so the thing is, if you have a good intuition or understanding for the whole idea behind Taylor series, then this is a super easy problem. Because even if, say, you're not any good at math, you should still have in your head that the whole idea behind Taylor series is approximating arbitrary functions with polynomials. But this function already is a polynomial. So what's the best approximation to this function with a polynomial going to be? It's already a polynomial. Is it an infinite polynomial? Well, yeah, kind of. You could say it's an infinite polynomial with most of the terms equal to 0, like most of the coefficients 0. So if what we have been claiming about Taylor series is right, which is that they're really just doing your best to approximate functions with powers of x, then this should already be its own best polynomial approximation. So if I tried to apply this formula, I would hope that I would just get back the same function. So let's check. I almost want to ask you guys, how many people think I'm going to get the same function back? All right, well, let's check. All right. So if I just went and plugged in the formula, so we're centering it at 0, which means we're actually doing the Maclaurin series, which is fn at 0, x to the n, over n factorial. So here, let me calculate a few derivatives. F of x is x squared plus 1. F prime at x is 2x. F double prime at x is 2. F triple prime, well, that's just 0. And all the other ones are also 0 after that. Okay, so f at 0, is 1. F prime at 0 is 0. F double prime at 0 is 2. F triple prime at 0 is 0, as are all the others. So if I plug these into this formula, right, nth derivative at 0 over n factorial times x to the n, which is f of 0 plus f prime at 0 times x plus f double prime at 0 over 2 factorial times x squared, f triple prime at 0 over 3 factorial x cubed. Okay, so let's see what we get. This one is 1. F prime at 0 is 0, so this term is gone. F double prime at 0 is 2, so I'll get 2 over 2 factorial times x squared. This one is 0. And in fact, all the ones after this are 0 because all the higher derivatives of f are 0. So simplifying this, I just get back to the original function. Oh, so like I did all this work just to get back to the original function.
X squared on the right.
Oh, okay. Robert pointed out, yes, I commuted the 1 and the x squared. Here, how's this? X squared plus 1. Okay. So actually, though, if you really understand the whole concept, this has to happen because the whole premise of a Taylor series was based on writing something as a polynomial. So this had to work out this way. It could go no other way. But maybe that's just because I was centering it at 0, right? Like this kind of looks like a Taylor series centered at 0. What would happen if I tried to do it somewhere else? Let's try centering it at 2. So we agreed the Maclaurin series, i.e. the one centered at 0, that one just gave us the same thing back. What if I center it somewhere else? How about, say, 2? Do you guys think I'll still get the same thing back? Anyone think I'm going to get the same thing back? No one? Oh, man. Well, let's see. Let's see. Okay, so if I now, the formula for it centered at 2 is fn of 2, x minus 2 to the n over n factorial. Okay, so, oh, here, let me just use these same formulas over here, right? I still have the same derivatives, so let me just calculate what is f of 2 is 2 squared plus 1 is 5. F prime at 2 is 4. F double prime at 2 is 2. F triple prime at 2 is 0, as are all the others after that. So I'm going to get, this is f of 2 plus f prime at 2 over 1 factorial times x minus 2 plus f double prime at 2 over 2 factorial times x minus 2 squared. All right, so let's see. F of 2 is 5. F prime of 2 is 4. F double prime of 2 is 2. And then F triple prime is 0, as are all the other terms. Okay, so this is 5 plus 4x minus 2 plus x minus 2 squared. Well, so I didn't get the same thing back, did I? Did I? Well, it doesn't really look the same. Could it be the same thing? Let's see what happens. So this is now just written out centered at 2, but if I multiply things out and distribute, maybe I'll get the same thing. So note, okay, I'm just going to expand this. So we will get 5 plus 4x minus 8 plus, and this will become x squared minus 4x plus 4. So I presume I get to cancel some stuff. Let's see. 5 plus 4 minus 8 is 1. Oh. Just get x squared plus 1. So all you guys should have raised your hand back when I asked if we're going to get the same thing. We do. It just looked a little bit different because it was centered at another point. But once you expanded it out, it turned out to be exactly the same thing. Okay, great. So it appears we have a self-consistent theory. And what you can take away from these two examples is that polynomials are their own Taylor series. All right. Now, I said that there's like a few functions which we better do the Taylor series for because they're so important. I already did some on Monday, which was sine, cosine, e to the x. I didn't do log yet, but I thought I would introduce it in a sort of roundabout way by way of an example and kind of a word problem. So this is going to be a long example that's going to show you guys a bunch of things if you pay attention. But I'm going to start with the formula for half-life, or actually like drug concentration. All right. If any of you guys are going to go into the medical field, pharmacology, you'll probably see a formula for the concentration of some substance in your body, in your bloodstream, remaining after a certain amount of time. And I'm going to give you sort of a simplified version of that formula, but the point is it decays exponentially is the rule. Like it cuts in half every 4 hours or something like that. Or, okay, so let's, example. A simplified model for the concentration of a drug in the bloodstream a time t after administration. I'm just going to give you guys a really, really simple model. Is the concentration, which I'll call C of t, is e to the negative t. Okay, it decays exponentially. Really simple model. You guys don't need to worry about the formulas. I'm just sort of providing a context here. Like, I don't know, did any of you guys go to Coachella? Oh, nice, all right. Or, okay, so let's say you go to Coachella or Burning Man or something. Like, I'm thinking about going to Burning Man this year, by the way. I was down in North Park last night, and I met a bunch of burners, and they said I should go down there and like present math lectures in Burning Man. That they said that there would be a bunch of burners who are like way into it. So they made a compelling case. I think I'm going to go this year. So let's say you just came back from Coachella or Burning Man, whatever, and you might have imbibed something, as one tends to do at these sort of festivals, but then you get a call from your dream job, okay? Like Google or Qualcomm, whatever, calls you up and it's like, we want you to come down for an interview. You've got 1 week. And you're like, oh, crap, because you're worried they're going to test you. Like drug test you, right? So you've got to do some quick calculations as to what concentrations are going to be left in your blood when you go down there. Now, I don't know if you guys know, like Google likes to do these cool sort of tests where like they'll give you some programming problem or something, and if you can solve it, they'll just hire you. So let's say because there are a bunch of burners over at Google, like Silicon Valley, they know. Let's say they give you an out. They say, all right, if you can calculate the half-life of whatever may or may not be in your blood without a calculator, you're hired. That's the problem. So I want you, all right, so problem. So I want you to solve e to the negative t equals 1/2, but I need an answer without a calculator, like a number, a numeric number. So like the first thing you would do to solve this equation is just take the log of both sides, right? ln of e to the negative t equals ln of 1/2. This side is negative t. This is negative log 2. So t is ln2. And if you had a calculator, you'd be done because you could just punch that in, right? It's like the easiest thing. But how do you get this without a calculator? Not so easy, huh? At least not until you learn Taylor series. Yeah, so we can use the Taylor series for log, which I haven't shown you guys yet. And but if we tried to calculate the Taylor series for log the same way that we've been calculating Taylor series, you would run into a problem right away. Okay, so what's the problem that we immediately run into if we try to just write ln x as a Taylor series? Why? Yeah, I know you know it. Yeah, you mentioned this after class last time. Anyone else notice like what immediately goes wrong? And I guess I said Taylor series, but here, let me say Maclaurin series because those are the easiest one. Just a Taylor series centered at 0. So ln x is not defined at 0. If you try to plug in 0, your very first term of your Maclaurin series is already infinite. So like you're screwed before you even got started. So there's a way around this, which is we don't quite do it for ln x. And the way it's typically done, so instead, we do a Maclaurin series for ln of 1 plus x. Okay, so this, let me just say, this one, so no Maclaurin series is possible for ln. Since ln of 0 diverges. So instead we do a series for ln of 1 plus x. It basically like shifts here. If this is y equals ln x, then this one is y equals ln of 1 plus x, and that's the one we're going to do a series for. So we need to come up with a series for ln of 1 plus x. But I've been mentioning that for a lot of these Taylor series problems, like there's a trick or a shortcut. So why don't we stick to what we already know? Now, we know, for example, x to the n is 1 over 1 minus x, our favorite geometric series. I showed you on Friday that by simply letting x go to negative x, we can get that 1 over 1 plus x is the sum of negative x to the n. And then, if you remember that log is the integral of 1 over 1 plus x, we can pretty easily just get the Taylor series for log by just take the integral of both sides. Right? So ln of 1 plus x, which is the integral of 1 over 1 plus x dx, that should be the integral of this series, which is 1 minus x plus x squared minus x to the third. Right? So it'll be the integral of all that. Which, according to our theorem, we can differentiate term by term to get x minus x squared over 2 plus x to the third over 3 minus x to the fourth over 4, so on. Oh, and then let's say plus c, some constant for integrating. You guys remember how we figured out what the constant was? When we have to do this is we would just plug in a point. So the easy point to plug in is just x equals 0. All right, so at 0, ln of 1 plus 0 is ln of 1, which is 0. On the right-hand side, what do we get if we plug in 0? Well, all the x's are gone. If we plug in 0 over here, every single term is gone except for the constant. So the constant's 0, which is nice. All that, and just the constant was just 0. Right? 0 minus 0 plus 0. 0. Whatever, minus 0 over 2 plus 0 over 3 minus 0 over 4, blah, 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 plus c. So that's just c, so c is 0. Okay. Thus, ln of 1 plus x is, we now have its Taylor series, or its Maclaurin series. It's x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4, so forth. So you guys see that trick? You're going to have to do it a few times on the homework, where it's like you know one Taylor series, and then you just integrate it, or sometimes derivate it, depending on the problem, to get a different Taylor series. But how does this help us with getting hired at Google, right? Well, they wanted us to evaluate numerically what the log of 2 is. And I just got a formula for log of 1 plus x. So if I let x equal 1, I get ln of 2 will equal, okay, so if I let x equal 1 here, I'll get 1 minus 1/2 plus 1/3 minus 1/4, so forth. Hey, it's our old friend, the alternating harmonic series. So I don't know if you guys remember, I actually told you this like a couple weeks ago, back when we were talking about the alternating harmonic series. And I told you that it was equal to log 2, but that maybe I would prove it or maybe not. I hadn't thought that far ahead in the course at that point. But I came through, and I proved it to you guys. So the alternating harmonic series adds up to the log of 2. And now, like, you can just add this by hand. Yeah, it's an infinite number of fractions, but hey, you're not using a calculator. Yeah, so done, you're hired. You're going to have an awesome life working at Google now, or Qualcomm, or whatever your dream engineering job is. Okay, that was that example. All right. I've been mentioning these shortcuts that you guys can use to solve these problems. So what if I wanted us to find a series for e to the negative x cubed? Say, let's say Maclaurin series, as usual. Now, if you tried to do this, oh man, I challenge you to try and do this by hand, straight from the definition. It would be brutal. It would get brutal fast. Start taking first derivative, second derivative, third derivative of this, and start plugging in points and see if you can somehow figure out a pattern for the coefficients. It would be a pain. So I said there's a shortcut. Anyone know what the shortcut might be? So here's a hint, is build on what we already know. And what series do we already know that could be helpful? How about in the red? Yes, you, ma'am. What series comes to mind that we know? Well, what's the one I'm asking for? The function I'm asking for is which one? What's the function in the question? What do we call these types of functions? If it's something to an exponent? Guys, what do we call something to an exponent? I'm asking for the power series. If you see e to something, the basic function to keep in mind is e to the x is our prototypical example. E to the x, the exponential function, is our prototypical example. And it's one that we've already done in this class. What was the series for e to the x? It was x to the n over n factorial. But I'm asking if that helps us to solve this problem. And it does. Here, you know what? Let me write this. How about instead of x's, let me use a different letter. How about e to the u is u to the n over n factorial. So this problem is almost totally solved for us if I let u equal what? Negative x to the third. And then I get e to the negative x to the third is, all right, so I'm going to replace the u with a negative x to the third to the n over n factorial. And, well, that's the answer. I mean, I can clean it up a little bit if I want. I could write it as, we like to pull out these negatives and put them to their own power. And then this becomes a x to the 3n. Yeah, so that's the answer. Right? That's the same as 1 minus x to the third plus x to the sixth over 2 minus x to the ninth over 3 factorial. Right, so not that bad, right? It's a lot easier than doing it the long way. But, all right, so now I want to run with this idea that we can just sort of use the series that we already know and plug in other stuff. And what I want to plug in next is a bit weirder than what I plugged in here. I want to plug in an imaginary number. Yeah, like while we're just like seeing all the things we can do here, let's ask ourselves, could I plug in an imaginary number to this series? So, right, like up until now, x is real, but what if, just ask yourself the question, I plug in ix, right, like for let's say for u in here. So the left-hand side becomes e to the I x. And then on the right-hand side, okay, so I'll just replace u with ix to the n over n factorial. So basically what I'm doing here is I'm using something that, strictly speaking, I haven't taught you guys. Right? Like, we did some stuff with complex numbers in this class. We did some integration with complex and, polar form and all that. I have never yet taken infinite series of complex numbers in this class. So there is something to be said about like the justification for is that even allowed. This class is not the place for that. So just for now, just take my word that yes, you can do this. The reason is that this series converges absolutely, which I showed you guys already. So there's probably a bit more to be said about that, but maybe that's for a class in complex analysis. Let's not worry about that. And just take my word for it that since this series converges so fast everywhere, that we're allowed to do this. So let me write out some of these terms. It'll be 1 minus ix plus ix squared over 2 factorial minus ix to the third over 3 factorial crap, here, let me write that up here, actually. So it's 1. Oh, I made a mistake. Sorry, this is a plus sign. Sorry, I made some, here, let me do this again. Here. Okay, so this is 1 plus ix squared over 2 factorial plus ix cubed over 3 factorial plus ix to the fourth over 4 factorial plus ix to the fifth over 5 factorial. Okay, so this is 1 plus ix. Okay, I'll get a I squared, x squared over 2 factorial. I cubed, x cubed over 3 factorial. I to the fourth, x to the fourth over 4 factorial. I to the fifth, x to the fifth. Okay. So we already practiced like what powers of I are equal to. So I can simplify this a little bit. Like this is a negative 1. This is negative I, right? Here, that's minus I, x to the third over 3 factorial. I to the fourth is just 1. I to the fifth, that's back to I again. And now let's try and write this like a complex number, which means we like separate the real and the imaginary parts. So notice that it alternates, like every other term is real, and then all the other terms are imaginary. This is, okay, so let me just take, okay, all the real terms are this one, this one, this one. These are the real terms. So that's 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. And then here, those are the imaginary terms. So if I just factor the I out of all those, I'll get, what do I get? I get an x. I get a minus x cubed over 3 factorial. I get a plus x to the 5th over 5 factorial. I wonder if anyone has seen where I'm going with all of this. Yeah. Yeah, we know both of these series. I did both of these on Monday. This is the series for cosine, and this, with the I in front of it, is the series for sine. This is cosine of x plus I sine of x, i.e., I have just proved Euler's formula. E to the ix equals cos x plus I sine x. Yeah. I think I told you guys like a month and a half ago I was going to maybe prove this. And I did, actually, finally. All right, sweet. So, you know, as a mathematician, I don't personally like hearing something that I'm just told to take for granted. So at least now you have some further justification for that formula. And this is about the simplest proof you can give of that formula. Of Euler's formula, that e to the ix is cos x plus I sine of x. Okay. See, I think I'm going to do one more super useful example for all you engineers. So, the last example that I'm going to do, maybe, I don't know, it's useful. I used it. So let's do the Taylor series for if f of x is 1 plus x to the alpha, let's find the Maclaurin series, and you're going to see I actually don't care about most of it. So f prime of x is alpha times 1 plus x to the alpha minus 1. F double prime of x is alpha minus 1 times 1 plus x to the alpha minus 2. You know what? I don't even care about any of the higher terms. So let me calculate some values. F at 0 is 1. F prime at 0 is alpha. F double prime at 0 is alpha times alpha minus 1. And I don't care about the other terms. So 1 over 1 plus x to the alpha has a Maclaurin series 1 plus alpha x plus alpha minus 1 over 2 factorial x squared plus, and I'm just going to call them higher order terms. And you'll see mathematicians and physicists and engineers write this when it's like, yeah, we don't even really care what these bigger terms are. Because, so Taylor series they're only necessarily valid locally, okay? So here's what I mean by that. We usually want x to be a small number when we're trying to approximate this function. Think of x as a slight perturbation. So these higher order terms, like whatever they are, they have higher powers of x. But think of x as a very small number. Then x squared is even smaller. X to the third is even smaller than that. Typically, you don't care. Like by the time you get to the third power, it's so small that it's like insignificant. It's totally insignificant for your calculations. In fact, and this is where this really gets useful, often you don't even care about the second power. Like x is so small that x squared is already too small for you to even care about. So what do you get? Thus, for small x, and what I mean by small, i.e. X much less than 1. Have any of you guys ever seen the double inequality sign? It means much less than 1. It could mean like x is, I don't know, less than 100th, for example. 1 plus x to the alpha is approximately equal to 1 plus alpha x. So I just threw away all but the first non-constant term in this approximation. And we do all this work building up the machinery of Taylor series, and then we just throw it all away except for the first sort of non-trivial term. And this ends up being 90% of the time, this is what you're going to use if you wanted to solve a problem. Let me show you an example. So, example, let's say I have the equation of a circle, which is y is equal to the square root of 1 minus x squared. And I want to approximate this circle right near the top, right here, when x is a small number. So use this formula. Use that 1 plus here. Let me use another letter. How about u to the alpha is approximately equal to 1 plus alpha u? Because this is the same as 1 plus negative x squared to the 1/2. So let u equal negative x squared. Let alpha, which is our power, be 1/2. And 1 over 1 minus x squared will approximately equal 1 plus 1/2 of negative x squared, which is 1 minus x squared over 2. Now, if I tried to plot that, so that's a upside down parabola. Let's see, it goes through the point when x is root 2. So if I tried to graph that, it would look like this. Now, okay, my drawing isn't perfect, but 1 minus 1/2 x squared is a really good approximation to the graph of the circle right near the top there. And I could do a little numerical example, but I think I've done enough of those, I think. I think you guys get the idea. So, yeah, stop right there.